Hello, everybody. My name is Adam Herrmann. I'm a PhD student at CU Boulder, and I belong to the AVS laboratory. Today, I'll be presenting to you Monte Carlo tree search with value networks for autonomous spacecraft operations. Before I begin, I'd like to thank my advisor, Dr. Hans-Peter Schaub, for his support in this work. I'll go through the motivation, problem statement, a problem formulation, the proposed solution, results, and a conclusion. Spacecraft operational autonomy. So, spacecraft operations planning is typically a ground-based activity, and this introduces limitations to operations and potential mission architectures. Spacecraft autonomy, however, is an enabling technology that can enable new mission architectures and improve upon pre-existing ones. Benefits of autonomy include reduced planning latency, reduced operational costs, and responsiveness onboard the spacecraft to unexpected events or opportunities. Challenges include limited onboard computation, verification and validation and safety guarantees, and proper problem representations and simulations to support the work. Of particular interest to spacecraft autonomy is the Earth-observing scheduling problem, which has been studied extensively in literature. In the EOS problem, one or more Earth-observing satellites must collect and downlink data to one or more ground stations. There are several variants that exist. There are single versus multi-spacecraft, single versus multi-ground station, and targeted versus area data type variants. This research considers single spacecraft, multi-ground station, and area target data types. The spacecraft simply just needs to point the instrument down at the Earth to collect as much data as possible and is target agnostic. Several solutions to this problem exist already. There's kind of rule-based autonomy, which is if, else, do this. There's optimization-based, which has been studied probably the most in literature. Mixed integer programming, simulated annealing, genetic algorithms, etc. have all been used. These formulations typically consider many targets or maybe many spacecraft, but they're computationally expensive. They usually consider limited dynamics, and they're forced to make linearity assumptions. However, reinforcement learning has recently shown promise, and in our laboratory, students have implemented reinforcement learning techniques on the Earth-observing scheduling problem, techniques such as proximal policy optimization or Q-learning. While training is computationally expensive, reinforcement learning is extensible to more conditions than simulated, and after training, agents can be rapidly executed either onboard spacecraft or in simulation. Motivation behind reinforcement learning. So recent successes of reinforcement learning have shown it's not only a viable technique for solving decision problems, but it can also be used to operate physical systems. One of my favorite examples is AlphaGo, which is a Go-playing reinforcement learning agent that beat professional player Lisa Dahl in a 5-game match in 2016, winning 4 out of 5 matches. This was a big success for reinforcement learning because it showed superhuman performance in an enormous state and action space learned on self-play alone. Another notable example is CAD2RL. These researchers used Monte Carlo policy evaluation on a vision-based collision avoidance navigation agent, which was trained on simulation data alone in Blender, but was deployed successfully on a quad rotor in the real world to avoid collisions with walls and other obstacles. In this research, we apply Monte Carlo tree search and state action value function approximation to the Earth-observing satellite scheduling problem simulated using the Basilisk Astrodynamics software framework. The MCTS and state action value function approximation applied in this research is similar to the work in AlphaGo, but slightly different. And the Basilisk Astrodynamics framework is a software architecture built by the AVS laboratory that's open source and used on spacecraft missions and for many other research things in our lab. Problem formulation. So we formulate an Earth-observing satellite simulation. Previous students in the lab have kind of wrapped Basilisk into an OpenAI gym environment. In this research, the goal is to maximize the data downlinked, whereas in previous formulations, it has been to maximize the data collected. A few Basilisk simulation parameters. These are detailed in the paper, but just at a high level here, it's a 500-kilometer orbit. We have a full attitude control, power, and data management system. The attitude control system includes reaction wheels and attitude control thrusters. The power system includes solar panels, batteries, a reaction wheel power model, an instrument power model, and a transmitter power model. And the data management system includes an onboard storage system, a transmitter, and an instrument that can generate data. We execute this on 90-minute planning horizons, mostly due to computational limitations, and we downlink data to 7 different ground stations around the Earth. As stated before, previous researchers in the lab have formulated the problem into a gym environment. This allows the agent to step through the Basilisk simulation by taking actions and then evaluating the reward and observation from that action to take more actions. One action lasts anywhere from 3 to 6 minutes of simulation time in a given mode. So for the charging, communications, and observation modes, these all last 3 minutes each, because that's about how long it takes for the attitude control system to settle attitude error to a negligible amount. The desaturation mode lasts for 6 minutes of simulation time, because that's about how long it takes to dump all the momentum in the reaction wheels. The nice thing about the gym environment is that it can be repeatedly reinitialized with a given set of initial conditions. This comes in handy for algorithms like Monte Carlo tree search that branch off of a current state to investigate different combinations of actions to see which returns the most reward. To do so, we cast the problem as a Markov decision process, which is defined by the 5-tuple, which includes the state space, the action space, transition function, reward function, and discount factor. This is a deterministic finite horizon problem. Finite horizon meaning that the simulation terminates at the end of a planning horizon when t is greater than t max, 90 minutes. The state space includes the position and velocity expressed in an inertial frame, the attitude error of the spacecraft in modified Rodriguez parameters, the angular velocity of the spacecraft expressed in the body frame. Big omega hat represents the reaction wheel speeds over their maximum allowable speeds. Z represents the percent charge in the battery. K is an eclipse indicator that can either be 0 or 1. D also is a percentage. It's a percent. B is also a percentage. It's a percent fill in the data buffer. H is the data downlinked in the planning horizon. Q sub j represents the access to each ground station. So there are 7. And P represents the percentage through the planning horizon that the agent has currently made it through. The action space includes observation, downlink, charge, and desaturation modes. For observation, the spacecraft simply points the instrument down at the Earth and collects data. For downlink, the spacecraft downlinks the data through an omnidirectional antenna to whichever ground station is closest and within view. For the charging mode, the spacecraft points its solar panels at the sun. And for desaturation, the attitude control thrusters are used to dump the momentum within the reaction wheels. The reward function is defined as follows. H sub I represents the data downlinked in megabytes for a given planning interval. And for a given planning interval, if Z equals 0, any of the wheel speeds exceed their maximum allowable wheel speed, or the data buffer overflows, that constitutes a failure. If no failure occurs, the reward is simply H sub I. If no failure occurs and the spacecraft reaches the end of the simulation, the reward is H sub I plus 1. And if the spacecraft fails, it gets 0 reward. The solution. So the goal here is twofold. First, we solve the problem using Monte Carlo tree search, and then we use the state action value function or estimates generated in Monte Carlo tree search to train a function approximator that can be rapidly executed, either in simulation or potentially onboard spacecraft one day. This algorithm here just shows how MCTS is executed within the simulation, within the simulation. So at each step through the environment, this select action function is called, and the state and the depth of search are passed in. After the environment is stepped through, a new state and reward are returned, and the process just repeats. How does Monte Carlo tree search work? As I stated before, at each step through the planning horizon, select action is called. Calling select action runs a predetermined number of simulations from the current state. So this essentially allows Monte Carlo tree search to branch off, try different combinations of actions, and select the next action that returns the most reward. Each simulation follows this select, expand, rollout, backup process. For selection, the action is selected that maximizes Q plus the exploration bonus U. If a state is reached that has not been reached before, the state action pairs are initialized for that state, and then rollout is executed, where random actions are selected until the end of the simulation. For rollout, the actions selected are random unless a ground station is within view, and then a downlink mode is initiated. And this is done to return the most reward possible. And after rollout, the reward generated during rollout and selection are backed up, and the process is repeated again X number of times, depending on how many simulations you want MCTS to run at each step. The second part of the goal was to use the state action value functions computed using Monte Carlo tree search to train a state action value function approximator. Q is a measure of how good a state, an action is in a current state S following a policy pi. It's defined as the expected value of the sum of all future reward given that policy pi, the state S, and the action A. This begs the question, what is the policy in Monte Carlo tree search that is being learned? It's a combination of two things. It's the selection of the intermediate Q functions plus the exploration bonus and the rollout policy. Monte Carlo tree search is executed a certain number of times to train the value function approximator on the data. So we run 5 MCTS training runs, complete training runs over the planning interval. The Q estimates generated from this, and it's typically about 1,000 for 5 runs, are then added to a training data set, which is used to train the neural network, and the process repeats. So more and more data keeps getting added to this training set, and the data set the neural network's trained on keeps growing and getting more representative of the problem. Results. Quickly, I'll go through kind of the experimental design here. So for Monte Carlo tree search, we vary the number of simulations per step between 5 and 50 to get a baseline of performance and determine how many steps, how many simulations per step we should select. We execute MCTS on 10 sets of different initial conditions. So this is, initial inertial position and velocity, charge in the battery, etc. And then we measure the total reward, downlink utilization, percentage of simulations successfully completed, and execution time. Then we train the value network on state action value estimates generated by MCTS on random initial conditions. And we greedily execute the value network on 10 and 100 sets of initial conditions. We first do the 10 sets of initial conditions to compare the performance to MCTS, and then we execute on the 100 sets of initial conditions. And both times we measure the same thing, the total reward, the downlink utilization, percent of simulations successfully completed, and execution time. So MCTS is able to finish every simulation to completion, which is great. So it takes in the resource constraints and is able to complete successfully. But each run takes about 3 hours to compute a solution, which really shows the utility of using the value network, which takes much less time. Performance seemingly degrades after 10 to 25 simulations per step. This is likely due to the fact that the exploration is generating suboptimal Q estimates, and some might be closer to the optimal Q value than others. Some might be higher than others that maybe shouldn't be. So suboptimal actions are selected. But in the end, this comes out to about a 5% performance difference, which I'm not too worried about. And given that 50 simulations per step generates much more data, we select 50 simulations per step. And also, I mean, the state action value estimates are just iterated on more. So, while they might not be optimal, I do think that there's value in having them iterated upon more. After 75 training runs, greedy execution of the state action value network matches or beats the performance of 50 simulation Monte Carlo tree search, at least in terms of total reward, and downlink utilization, which is fascinating that the value network can perform better than the MCTS algorithm that trains it. I'd say this is probably due to the fact that it's trained on so many diverse initial conditions. However, where MCTS outperforms the value network is in the percentage of simulations completed. So the policy that the value network ends up learning is essentially to collect as much data as quickly as it can and spend the rest of the simulation downlinking it, ignoring the resource constraints like battery, an empty battery, or a buffer overflow. This is definitely a problem that needs to be addressed. But one benefit to using the value network is that the execution time is on the order of 7 seconds, which is orders of magnitude lower than Monte Carlo tree search, which takes 3 hours. The value network was also executed on 100 initial conditions to get a better picture of performance, and it's more or less the same as the comparison to MCTS on the 10 initial conditions. Not much has changed. On average, reward is slightly lower, but in this initial condition set, there are actually planning horizons where there are no downlink opportunities. And while those might, I think those are important to include because it shows that the state action value network can still execute to completion even if there aren't any downlink opportunities available. Similarly, the percent of simulations that succeeds kind of tanks as the training goes on, and this is due to the learned policy. So conclusions: Monte Carlo tree search is a useful tool for ground-based planning at the very least, and value function approximation could be used for onboard planning given enough computational resources if simulation failures are guaranteed not to occur. So a lot of work is going to need to go into this in the future. Different reward functions should be investigated. There are a few different ways that these have been formulated in the past in the lab that are different from what I did that I'd like to try. Maybe larger success bonuses or larger penalties for failure. Also use greedy value network execution within Monte Carlo tree search as the rollout policy. That's what AlphaGo did. Worked out quite well for them. It might work very well here because it allows the state action value estimates to get continually iterated on. I'd also like to explore a discounted versus non-discounted reward. This is a finite horizon problem, so discounted reward may not be appropriate. And I'd also like to compare to optimization-based techniques to see in which ways MCTS and value function approximation really shine. Like to look at longer planning horizons and also just reduce assumptions made within the simulation. So thank you for listening. Normally I'd take questions now, but I will be at the Q&A session. So if you have any questions, please attend, and you can scan the QR code here and it will take you to the ABS website. So thank you for your time and have a nice day.